Hello friends and welcome back to my YouTube channel. So this is the third set of solutions of the CSIR-NET examination which was held on 26 November 2020 in mathematics stream. So let's move on to the questions one by one. So this question you can see it was actually a question regarding the idempotent matrices. So we are given a matrix for which p square is equal to p and we were asked to find out which of the following options are correct. You can see there are 4 options given to you. So if you consider idempotent matrices, we know many things about idempotent matrices. The first and foremost thing which I would like to mention here to crack this problem is nothing but regarding the eigenvalues of an idempotent matrix. So if you take idempotent matrices, the eigenvalues are basically zeros and ones. It will have only eigenvalues as zeros and ones. So its characteristic polynomial, suppose you take P to be something like an n by n matrix, then its characteristic polynomial is nothing but equal to x minus 0 power sum n1 into x minus 1 power sum n2, where n1 plus n2 will be nothing but equal to your n. Order of the matrix is basically n. This is nothing but the characteristic polynomial. Similarly, the minimal polynomial is nothing but equal to x minus 0 into x minus 1, or we can write as x into x minus 1. So since this eigenvalues, you can see the minimal polynomial is actually a product of distinct linear factors. This matrix P is actually a diagonalizable matrix. That means idempotent matrices are basically diagonalizable matrices, and that will give us a lot of properties which will help us to crack this problem. So you can see here, as I told you, the eigenvalues are basically zeros and ones. So we are given an option like they have negative eigenvalues. So this option goes wrong because we have zeros and ones as eigenvalues. Now if you take this second option, that's all eigenvalues are basically imaginary roots, like complex imaginary roots, but you can see they are zeros and ones, so basically it's also not a true option. Now if you think about the trace of this particular matrix P, so whether it is an integer is the question. So you can see obviously the eigenvalues are zeros and ones, so we are going to guess definitely the trace to be actually an integer itself, because your trace is nothing but the sum of the eigenvalues of that particular matrix. So this question, this answer is true. Now what about this first option? You are given that trace of P is equal to rank of P. So I've already told you enough data to argue this statement. I've already given you what is a minimal polynomial, and we saw that it was actually a product of distinct linear factors, so it is diagonalizable. So if it is diagonalizable, what you have? Yes, we have something like the algebraic multiplicity of an eigenvalue of this matrix will be equal to the geometric multiplicity of that particular eigenvalue. So that means if 0 is an eigenvalue, that means since the matrix is diagonalizable, the algebraic multiplicity of 0, that means how many times 0 is repeated as an eigenvalue, it is equal to nothing but the geometric multiplicity of 0. That is the eigenspace, dimension of the eigenspace you can take of 0. It is basically 0, or the number of linearly independent eigenvectors corresponding to 0 will give you the geometric multiplicity of 0. And what is the geometric multiplicity of 0? That is set of all eigenvectors x for which ax is equal to 0 times x. That set, its dimension is not known as the geometric multiplicity. So ax is equal to 0x means ax equal to 0. That is set of all x you take for which ax equal to 0. That set you take, its dimension is nothing but the geometric multiplicity of 0, right, as an eigenvalue. So here you can see it's also interpreted in some other way, that of all x for which ax is equal to 0. That means it's nothing but the nullity of the matrix A, right? So if you find out the geometric multiplicity of 0 here, it's nothing but the nullity of the matrix A. And also we know a very interesting result about this rank and nullity. That is, if you take the matrix P, rank of P plus the nullity of P, if you take, it will be equal to the dimension of the number of columns in the matrix M, P, that is nothing but equal to n. So now if you consider the number of times our 0 is repeated, that is geometric multiplicity of 0, and if you try to find out the trace of P, then it is, we can write something like this, that is the trace of P will be nothing but equal to the total number of eigenvalues n minus the geometric multiplicity of 0, right? That is, suppose you diagonalize the matrix P, that is you get a D matrix to be something like this, diagonalized form of P. Say you have some other like you have chosen a non-singular matrix for which A inverse P A is equal to D, and this, in fact, this A is constructed using the eigenvectors of the eigenvalues here. So when you take this consider case, you can see when you have the diagonalized form here, the trace of A is nothing but equal to you can see how much times you get, number of times, there is a number of times 0 is repeated exactly, geometric multiplicity of 0 times, and the remaining will be in fact 1. So the total trace you can write it will be equal to something like n minus geometric multiplicity of 0, right? And this geometric multiplicity 0 is nothing but what? The nullity of P. So n minus nullity of P, and we have this result that rank plus nullity is equal to n. So n minus nullity of P is nothing but what? Rank of P. So this directly will get us equal to rank of P. So this is also a correct option in this question. This question is basically a question from part C. So keep it in mind. It's like we have two correct answers in this particular question. One more doubt which we can have is that you can ask me that, like, why don't you consider identity matrix? I square is equal to I. We know that if you take identity matrix of order n here, we get I square is equal to I, and only the eigenvalues are actually ones, right? We don't have any zero eigenvalue. But in that case also all these things are valid. Okay, so I think that's this question, and let's move on to the next question. Now we have an interesting question. You can see here we asked the following is actually a bijection with R. Like, if you consider the functions from set 0 1 to n, set of natural numbers, or the functions from n to set 0 1, set of all subsets of n, or set of all subsets of R, which one is actually in bijection with R? So I'm going to use the idea of cardinality to crack this particular problem. We know that if you take set of all functions from A to B, and in that case the number of functions will be nothing but equal to cardinality of B power cardinality of A. So total number of functions we can find this form. So that idea we can use here to crack this particular problem. So we know that set of natural numbers, we take the cardinality to be something like LF0, and the cardinality of R will take something like C, the continuum. Okay, so suppose if you take suppose you're taking option C, set of all subsets of n. So what we have is nothing but 2 power LF0 is a cardinality, and if you suppose you take set of all subsets of R, we'll get something like 2 power C, where C is the continuum. And also if you take the set of all functions from n to 0 1, again you get something like 2 power LF0. And if you take the first option, that is functions of set of all functions from set 0 1 to n, again you are going to get something like LF0 square, or LF0 times LF0. So if you, and we have one more result that the continuum is actually nothing but equal to 2 power LF0. So now we can easily argue which is the correct option in this case, because set of all bijections on R, which is the following is actually a bijection with R is a question. So R is basically with cardinality C. So which is the correct option? Yeah, so the correct options will get us this and this. So in this question we got two correct options, option B and option C. So now let's move on to the next question. So you can see this was actually a question asked from part A, that is if f of x plus 2 is equal to x plus 1 raised to 34 minus x plus 1 raised to 33 plus 5, then we are asked to find the value of f of 0. So here you can see to find f of 0, what you can do is if you substitute x equal to minus 2, what you are going to get? F of minus 2 plus 2 is going to be something like minus 2 plus 1 power 34 minus 2 plus 1 power 33 plus 5. So that is nothing but minus 1 power 34 minus of minus 1 power 33 plus 5. So this is going to be, you can see the even power of minus 1 is going to be 1, and the odd power is going to be minus 1. So minus of minus 1 is will become plus 1 plus 5. So we'll get the answer as 7. So it's a very simple question, right? So now let's move on to another question from regarding actually the linear programming problem. Basically it's actually a problem from operations research. You can see we are asked to find the maximum and minimum value of say z equal to 5x plus 7y with the constraint given to us is actually mod x plus mod y is less than equal to 1. See, every exam there is at least 2 questions asked from operations research, and the level of the questions they are asking is actually very simple. So I would prefer you to please also look at these operations research problems. Don't skip those problems actually. So if you can see here, we have to maximize or minimize this particular function 5x plus 7y, and the region, actually how we do the problems, basically we using the constraints, we find out the feasible region first, and we have a theorem that that in the maximum and minima will be attained in the corner points or the border points of the feasible region. So here actually the feasible region we have to find using the constraints given to us. So we given one particular constraint here, you can see it's mod x plus mod y less than equal to 1. So we need to find out the area first. So okay, you're familiar with this area. Actually it is nothing but bounded by 4 lines, right? This can be written, actually we will get 4 lines basically. That is, if you take mod x plus mod y equal to 1. So let's try to find out the feasible region. So we'll have this region, this line x plus y equal to 1. Then we'll have x minus y equal to 1. Something like this, x minus y equal to 1. This is the line x minus y equal to 1. Then we have something like y minus x equal to 1, or minus x plus y, sorry, minus x plus y. This is the line minus x plus y equal to 1. And then we have the next one is basically sorry, this is not actually minus x plus y. I think the minus x plus y equal to 1 line is this one. Okay, so we just have to plot these lines, and we have minus x minus y. So minus x minus y, so minus x minus y equal to 1. This is the line. So this is the area, and we are actually asked to find all x and y for which mod x plus mod y is less than equal to 1. That means the area what we are going to get is inside. So this is the feasible region we will be getting in this case. Usually this is how we do in our linear programming problems. When we solve, we do in this manner. We'll be given constraints, and using the constraints we'll be finding the region. First we'll be drawing the lines, corresponding lines, and then we'll be finding the region inside, because we are asked to find set of all xy for which mod x plus mod y is less than equal to 1. So if I take a point 0 0, you can see mod 0 plus mod 0 is less than equal to 1. It is satisfied. Suppose if I take a point outside somewhere, say something like 2 0, then you can see something like mod 2 plus mod 0 is 2 plus 0 is not less than equal to 1. So this point is not inside this. That's how we find the region also. Now what we have to find, the result says nothing but, like, we have a result in operations research which says that this maximum is basically attained on the boundaries. That means in the corner points you can get the maximum or minimum values, or on the boundaries. So in this case you can see we need to find these points exactly where we have these lines are touching. So you can see this is the point basically 1 0, and this is the point actually 0 1. This is the point minus 1 0, and this is the point 0 minus 1. So we can expect the maximum and minimum values at these boundaries. So if you take the 0 1 value, or if you write down all the points 0 1 minus 1 0 1 0 and 0 minus 1, and if you find the value of 5x plus 7y, 5x plus 7y, you can get the answer. So you get 5 times 0 plus 7 times 1, 7, minus 5, you get here as minus 5. So at this particular point you will get as 1 0, that is 5, and at this particular point you get as 5x plus 7y is equal to minus 7. So now you can see where we get the what are the maximum minimum values it will attain. So the maximum minimum values it will attain is actually nothing but 7 is the maximum value and minus 7 is the minimum value. So in this question this is the correct option. Okay, so what I've done is simply I've just drawn the area there, and I've tried to find out, I just applied the simple theorem what we have, the result what we have, that this maximum minimum will attain in these boundaries. So that I have used, and I found the answer here. So now let's move on to the next question which is asked from same examination. So in this question you can see it's actually a partial differential equation is given to us, and we are asked to get the solution of this particular partial differential equation. So what we have is an partial differential equation of the form something like px plus qy is equal to some r, where p is nothing but dou z by dou x, and your q is nothing but dou z by dou y, and r is basically 0 here. So it's actually a Lagrange's linear partial differential equation. So we can just solve it by this method. Dx by p is equal to dy by q is equal to dz by r, and we can just get two functions u and v, and the final solution can be written as something like phi of uv is equal to 0. So if you try to solve this particular problem, you'll get something like dx by x is equal to dy by y is equal to dz by 0. So from that we directly get one equation, that is z is equal to we get dz equal to 0, or we get z is equal to some c1. And if you compare these two, we get something like dx by x is equal to dy by y. Then we can write something like, that means if you integrate log x is equal to log y plus say some constant, so I'll take this log c1. So from which I can get something like x is equal to c1 y, or we get c1 is equal to something like x by y. Okay, so yeah, not c1 y, I'll take c2y. I'll take here c2 as a constant, not c1. So now we got two cases here, and now we can write down the solution. Yeah, so what we get the solution? We get the solution to be something like, say, c1 equal to phi of c2, or we can write something like z is equal to phi of x by y. So that is the solution we have found in this critical case for this particular partial differential equation. So now actually I'll be coming with the remaining questions also. As soon as I get the questions, I'll be putting the solutions there. So those who are for first time using this particular channel, or my channel, visiting my channel for the first time, so I would request you to please subscribe my channel and please like and share this video. Thank you so much.